Okay, thank you, Alex. It's my pleasure to be here. As you can see, I'm from engineering. So I have a lot of friends in mathematics. I guess that's why I'm here. So I'll talk to you today about a problem that we need something beyond fractional mechanics to study the material failure. And this is particularly the case for brittle materials. And so just a little bit motivation on why do we need this work. This is an example of how brittle material fails. This is concrete material. A lot of our infrastructure are made of brittle materials, even ceramic for protection, armor protections. They're very brittle, right? So for these kind of materials, when it fails, it has a lot of cracks in there. There are many, many cracks, millions of cracks. From very small cracks, they grow and they form bigger crack, and then up to the structural failure. So try to model every crack by the conventional fractional mechanics is very challenging for this type of problems. And so if you look at traditionally how material failures are modeled by mechanics, there are two approaches. The first is a fractional mechanics approach. I call it a discrete description because you do need to model every single crack. You need to know where the crack tip is, where the crack surface is. So you then, in your solution, properly introduce jump condition, singularity at the crack tip and all that, right, to model these problems. So you need to take care of all this roughness of the solution. The mathematical models for fractional mechanics are based on energy principle, for example, the Griffith's energy. Things like that, they are very much geometry driven, as I said, depending on the crack size, the crack orientation, the crack tip location, the distributions. And you have to model every single one of them. Okay? And it can be easy to understand that the solution is strongly mesh dependent, because as the crack grow, it may not grow along the element boundaries where you can just open up the element. It may go into the element. So different mesh orientation, mesh density will, typically result in different solution. Of course, as you refine the mesh, and the solution will essentially converge, but you need a lot of mesh refinements. Very hard to deal with even three-dimensional crack. A few three-dimensional cracks will be very hard to model, leave alone crack propagation. Now then, of course, the other school of methods to model material failure is by damage mechanics. So this is, in a sense, the mixed way or averaged way, smear type approach to look at the density of material, failed versus total volume. Right? So in a sense of density of material failure. And therefore, this makes it a continuum approach or continuum description of material failure. The strong discontinuities are reduced to weak discontinuities. The mathematical models are usually phenomenological. Okay, so again, you argue how do you get the form, how do you obtain the material constants and things like that. And then when material fail, described by damage mechanics, there's a so-called softening response that's going to happen. So if you look at the simple, say, Hooke's law, right? You pull a material in tension, and as you apply the force, and the displacement gets bigger. But once the material fails, then it will drop. Okay? So then the stress strain curve or the force displacement curve will have a hardening curve and then softening. In that softening region, as you can imagine, now the derivative become negative. Okay? So in a simple term, the material now have a negative Young's modulus. Okay? So that will then change the type of PDE. If you have an elliptic problem, it now will become, it loses ellipticity, depending on whether you consider the dynamic effect or not. But typically, then you lose ellipticity. So mathematically, the problem is ill-posed. And there's really no unique solution unless you find a way to regularize. Right? So there are all these issues need to be addressed. And when this happens, it's like a bifurcation problem. Any perturbation to the solution will lead the solution to a different path, a very different path. And mesh is a discretization, certainly introduce perturbation to the numerical solution. So the problem is extremely mesh dependent. In fact, this mesh dependency is much, much worse than the mesh dependency you have here for fractional mechanics, simply because the problem is ill-posed. And if you refine the mesh, the solution, in fact, never converge unless you do something about it. And this is so I would like to address primarily these two topics today. And in the literature, there's a very large body of papers and books being published to address these issues. Even I think until today, this is still a problem that is difficult to solve. So what I'm trying to do here is to look at fractional mechanics. This is almost like a first principle in, of course, not the real first principle, but it's really something that is most basic. Can we do something along this line and then try to link fractional mechanics to damage mechanics? If I don't have to deal with the whole structure, if I just take a sample, say representative volume, then it is possible that I can still afford to use fractional mechanics. And I'll see how I can link from fractional mechanics, from a sample, and extract some damage law and use damage law for upper scale calculation. So that's what we are trying to do. I use the term homogenization, really not is in the very general term, not really in the traditional way of homogenization, scale separation with this asymptotic type of connection. I'm not doing that. I'll show you how we do it. And so if I can connect fractional mechanics to damage mechanics, then hopefully I can then take a sample of materials and I will construct an approximation functions to solve these problems. And I will look at its free energy and how I connect this to the damage mechanics. So hopefully I can construct a damage law for upper scale calculation. Okay, so with that, what I would like to talk today is I'm going to start with the energy bridging between fractional mechanics and damage mechanics. And then I'll talk about the micro-crack-informed damage model. So now these damage models are then constructed not by phenomenological assumptions, but really looking into the microstructures. Okay, so collect all the information from the smaller scale. And it turns out that we can explain the mesh dependency by something called the size effects, and I'll explain that in a few minutes. Size effects has been applied to in mechanics and materials in many different fields, but I think we can also explain the mesh dependency by size effects in damage mechanics. And I'll share with you some of our thoughts in that area. And then, as I said, the problem is ill-posed. So one way to regularize the problem is to introduce a non-local representation of the deformation. And so I'll talk about that. As an engineer, I think I have no excuse not to show applications. I have to show you application to show that I'm an engineer. So let's start with something, just elasticity. Okay, so I have an elastic body here. Knowing that the material, it's something like concrete or ceramics, there's a lot of defects or imperfections in the materials. If you zoom in, then you see the microstructures. Typically have some voids in there, some micro cracks in there already exist. This happens during the processing of the material. So there's nothing to avoid that. They are there. You have to take that into account. Of course, if I have to take all the details into consideration and try to resolve up to that length scale, and so here I use epsilon here, that means that I have to try to resolve the total solution, which is, of course, computationally very expensive. So the idea here is I will try to look at the Helmholtz free energy in the microstructure. I will do a numerical experiment, like what you do in the lab, but I'll do a numerical experiment. I hope I can model all these microcrack propagations in the microstructure. Then I'll compute the free energy. I'll use the history of free energy with respect to the homogenized strand and extract some damage law out of it. Okay, so that's the sort of rationale here. So hopefully through this process, I'll be able to now solve the problem at the upper scale. But the stress and strain relationship are then constructed from this Helmholtz free energy. Okay, so this will be the key of this whole process. As long as I can obtain this, then I can solve this elasticity equilibrium equation with damage law at the upper scale. Okay, so with this in mind, I would like to get down to something very basic, because I'm not sure everybody here knows stress and strain, so let me go with something really simple. It turns out that for a representative volume of materials, and if you have cracks in there, then one needs to take that seriously, because you can't just do an averaging, okay? And it turns out that if I have a cracks in the microstructure, and if you look at so-called homogenized stress, which is by definition based on the traction or the applied stress on the surface of the microstructure and to a boundary integral. That's a definition of the homogenized stress. And it turns out that even with cracks in the microstructure, homogenized stress is nothing but an average stress. Very easy to show that. You just average the stress out, you get the same thing, even with cracks in there. But strain, it's a different story. Homogenized strain, which is by definition taking the displacement on the surface of the RVE and integrate over the surface of the microstructure. It's not the same as the average strain, but there's additional term which accounts for jump of displacement field across the crack surface, okay? So if you take this into account, then you can work out the free energy in the cracked microstructure, right? So free energy is stress times strain, and then you bring in the definition of strain, which is a gradient of displacements. You apply divergence theory, and then you can then transform this to a boundary integral. And this particular term, if you do some manipulation, bring in the definition of homogenized stress, which is by traction from the boundary. You bring that into here, you can show in the end this, I think it's a very important equation. What it says is that the Helmholtz free energy in the cracked microstructure is right here, plus the surface energy is equivalent, in a density sense, divided by the volume, is equivalent to the free energy of this homogenized continuum. Okay, and the homogenized stress and strain are defined, as I said here. Okay, so what do we do with this relationship? So if you have this relationship, then what I can do conceptually, okay, so I'll get into the details, but conceptually, I will take a microstructure, I'll take a representative volume of the material, so with some cracks in there, I will then apply some stress or some display or some strain on the surface of the microstructure. I'll properly, hopefully, be able to simulate the crack propagation in the microstructure. Then I'll compute the Helmholtz free energy in this cracked microstructure plus the surface energy. And I'll then assign this as the Helmholtz free energy history of this homogeneous continuum. Then I will show you then how do I then take this and extract some damage laws based on thermodynamics. And then hopefully with that, I'll then be able to use that for the continuum scale calculation. Okay, so that's the logic here. All right, so be able to model. So I have to be able now to be able to model all the crack propagations in the microstructure. And a good candidate to do that work is this reproducing kernel particle method, RKPM, and the pioneer of this work is Wing-Kem Liu here sitting in front. So let me roughly describe this, and I apologize for those who already know this because it's very well known, but just for the sake of completeness of my presentation. So here, the domain is discretized by a set of points. Okay, so there's no mesh behind it, it's by a set of points. And for each point, for example, point I here, you can define a domain of inference or open cover, okay? Open cover associated with each point. So this is almost like a horizon in paradigms, okay? So you define some sort of domain of inference, and you have to make sure for all the points you integrate all the domain of inference. It will have to cover the total domain, okay? So that's a minimum requirement. Now, if then within each open cover, I will construct a partition of unity. Okay, partition of unity meaning that for every open cover, I have a partition of unity associated with that, and they have to sum up to 1. And this is nothing but an exact representation of a constant field, right? So you have the first order truncation error, and that's the minimum requirement for solving second order PDE to show convergence. Okay, so that's a minimum requirement. But of course, with this, it's very simple. Shepherd function will do the job, right? Every function, every open cover, you have a function, you just divide by the sum of all the functions. Of course, they sum up to 1. But of course, this converges really slowly. And that's the main idea of this so-called reproducing kernel approximation. The partition of unity associated with each open cover is constructed this way. This multiplication of 2 functions. The function in the blue color is called a kernel function, which is something like this, okay? And the support can be circular or it can be rectangular if you do have an isotropy or whatever very strange geometry. You can use a different shape, but usually one will use a circular shape of the open cover. And you construct, let's say, for example, use a spline function, okay? And so this is called a kernel function. And as I said, if you simply just take this spline function and divide by the sum of all the spline, then you get the Shepherd function, and you have partition of unity, but that converges slowly. So the idea here is to correct this. So if this is just a normalization, then you get the Shepherd function. Otherwise, you can introduce some sort of monomials and multiply by the coefficients. The coefficients are not constants, so that's something so I think is very unique here. The coefficients associated with all these monomial bases are function of x, y, z. Okay, that means depending on where you're approximating the function, the coefficients are allowed to vary. Okay, and that has, as you can see, has a notion of so-called moving these squares. You don't just do a square, these squares fit. You allow the coefficients in the least square fits to vary in space. Okay, so now, of course, so how do I obtain the coefficients here? Now, one thing which I also feel is very unique here in this original idea is, as you can see, you can have this kernel function that you can take different forms of smoothness depending on the physics that you're dealing with. Okay, so for example, if you are dealing with crack like I'm doing right now, then I'll do something like a step function, something that's introduce discontinuities, right? So that you get the right regularity in the approximation. You can do something like a C0 function, like a, C0 finite elements, right? A head function will give you a C0 continuity. You can go to C1, go to C2, you can go to Cn. This comes free, unlike FEM, as you know, because they have to be conforming. Therefore, continuity has to be imposed along the element boundary. And just to get C1 in 1D, you have to use up to third order polynomial because you have to have more terms to make sure the derivative is continuous. So every time you increase one order of continuity in FEM, you pay for it by increasing the order of polynomials. But here, you don't have to. These two are entirely independent. I can have a very smooth kernel, say C5 spline, and I can simply, if I feel that linear basis is enough, I'll use linear basis here. If you use FEM to C5 in 1D, I think you have to have 2n plus 1, 11. Very expensive, right? But here, you can do something really flexible. Or if I wanted to have roughness in approximation, such as crack, then I use something discontinuous here, and I can still have any order of basis that I prefer to use. So I think this is something that is very unique. Also, it makes it very unique to add points, adaptivity, and things like that. But anyway, so once you make your decision on the continuity of this kernel and the order of basis here, Then to obtain the coefficients, you enforce this approximation to exactly reproduce the basis. Right? So if I have m set of bases, I will have m set of equations here, and that allows me to solve for the coefficients b. That's it. And then the rest is just algebra. So that in the end, so you solve for b, you plug it back in here, then you have this reproducing kernel particle method, the approximation function for that. There's also mathematical analysis. As you can see, this rate of convergence is very similar to what you have in FEM. This is the Sobolev norm. And so I have n plus 1. N is the highest order complete set of monomials here. So you have the same rate of convergence in FEM, of course, is h here. But here A is the sort of open cover, the support size. Okay. But other than that, I think you get very similar rate of convergence, but the constant C here can be much smaller. If you're solving a smooth problem, and I choose smooth base, a smooth kernel, it really helps you to cut down, reduce this constant C to a very small number. If you're dealing with a rough problem, then you choose the proper kernel. You capture the right roughness in the solution. And again, this constant C can be much smaller than what you have in FEM. Okay, so with this in mind, then of course, then you plug in this into Galerkin equation, just like a standard FEM. You have a strong form, you construct the weak form, introduce Galerkin approximation, and then you have to do quadrature. Right? So quadrature itself is an issue, and we've done a lot of work, but for today's talk, I would not cover that. Just assume that I know how to do quadrature. And now to model the crack problem, you can do it different ways. The first approach is like this. You will do that in extended finite element method. You can borrow that idea. This is the reproducing kernel approximation, maybe smooth, maybe non-smooth. Let's say I use a smooth kernel. So this one is smooth. Then I'll add the Heaviside function to introduce discontinuity across the crack surface. And I have the crack tip asymptotic functions that you can obtain from the linear elastic fracture mechanics, because at the crack tip, the behavior is always the same. Regardless of the geometry, regardless of the boundary condition, near the crack tip is governed by these functions. Right? So you can bring this into the near tip. Near tip is just sum over a few points near the crack tip, and that will help to enrich the solution near the crack tip. And make sure that you have partition of unity and all that. That's one way to do it. The other way to do it is to go back to this, is to bring in those crack tip asymptotic functions here, right? And have a coefficients associated with each one of those. So you pay for it by solving the local system first. So now you have to reproduce not just polynomials, but also the enrichment functions. So you pay for it locally, and then you apply that to the global sense. Okay? So that's the way to solve, to model crack problem. And so here, I just give you an example. I just skip all the benchmarks. So we have check compared to analytical solution. Look at the rate of convergence, by the way. If you have the near tip asymptotic function, the rate of convergence can be the same as the smooth problem, because the near tip solution already been taken care. So the solution error actually comes from the smooth part of the solution. So the error behaves like a standard. If they say, if you use linear basis, you get L2 rate of convergence of 2. Unlike other methods, it reduces to 1. Here, if you have the basis, you get the right optimum rate of convergence. This is in tension. You take the sample, apply tension, apply shear, and so again, this is a more complicated problem. But just to show now, we apply this to applications, but the convergence and all that has been studied. Okay, so now I can do this, right? So, so with that, I will be able to now compute a complete history of free energy within the sample. And now I'm going to take that. So this is my computation. Right? So I can do all this computation. I have this free energy, and I can now use that to extract some sort of a damage evolution functions out. So let's go with something, the simplest one, the singular, or the scalar damage model. It's just one damage parameter, right? So this is the undamaged Helmholtz free energy. This is the one through computation with all the cracks in there, model all the crack propagation. So I have a complete history of that as a function of homogenized strength. And so from here, as you can see, you can easily then extract the history of this divided by the undamaged free energy, and I'll get the evolution function for this damaged parameter. Right? So this is through computation, and every different microstructure will give you a different curve. Yes.
For large deformation?
Yes, because it's a large rotation. So yeah, all those are taken care of. Well, then if you have more complicated material like a concrete, it fails very differently in compression, in tension, in shear, then you can do something more comprehensive. For example, there's one proposed by Michael Ortiz. I think Ortiz is not here yet. That's some work that he had done a long time ago. And he proposed this. He proposed this Helmholtz free energy function, where he decomposed the free energy into tension and compression. And tension and compression are defined in the eigenspace of the stress tensor. Okay, so you look at the eigenvector, eigenvalues, and then you separate the space into tension, compression, and then you construct them separately. Again, if you choose to use these kind of free energy, then each one of them will have a damage function, one for tension, one for compression. Again, this one is by computation, and then you can then take the finite difference and extract the damage evolution functions out for tension or for compression. Of course, you can do something fully tensorial, right? So with this framework, now if I can extract a fully tensorial damage model, again, the red one is by computation. From thermodynamics, then you can compute the energy release rate from here, and you simply, again, you can take finite difference, this one by computation, and this one is the undamaged free energy, and you can then extract the fully tensorial damage model. Right? So if necessary, you can do this. So the framework is here. All right, so with this, I just show you some examples. So here, you take different samples, and of course, as I said, different samples with different microstructures, different samples with different microstructures, then you get a different damage curves. Right? So you can do this entirely based on the real material images. Here, we take 100 samples, so you get 100 curves. They behave similar, but different microstructures does give you a different damage curve. And now you can use this for structural scale computation. One can now introduce stochastic representation of the material model, since now you can have from here extract stochastic properties, and then you can have now a material model that is stochastic, okay, if you choose to do so. Okay, so this is one application. We use this to study the interface failure mechanisms between the reinforcement and either the cement or the ceramic material. And this is a ribbed rebar. And as you can see, as you pull it out, then it forms a damage zone starting from the rib location, and it propagates. Okay, so you can now study this, and we actually use this to construct another damage model. That damage model is for the debonding between reinforcement and the matrix material. Right? So then once you have this, you can use this to do various different things. This is one application, to get the debonding damage model for composite material. Okay, now it turns out that there's a size effect. Okay, so things never been ideal. So there's something that is actually causes a lot of headache. And I'd like to explain what's the cause of the problem and see what we can do about it. It turns out there's a characteristic length in this damage model. And let me explain that starting from the principle of minimum potential energy. Okay, so assume here I have a deformation state E, and that's the deformation in equilibrium. If there's a perturbation, any perturbation from equilibrium, I call it head. Okay, so all the quantity whose head are the ones perturbed from equilibrium state. And you can take the difference between these two, and this is a material elasticity tensor, which is positive definite. Okay, so this term is positive. This is just a quadratic form of this, positive definite. And then on the crack surface, assuming I'm using the cohesive law. Okay, so cohesive law requires a jump of displacement field, and then there's a cohesive coefficient K prime, which is also usually positive. Positive definite, a positive semi-definite. So the sum of this will be always greater than or equal to 0. And so now if you then separate it out, and then you bring in the relationship that the surface traction is in equilibrium with the stress computed from the displacement field that is in equilibrium. If you take that into account, and also use the relationship between the cohesive law and the surface traction on the crack surface, then you can arrive this equation, which is no surprise. It just simply say that any perturbation from the equilibrium state will increase the potential energy. And here we simply just show that this is also the case for fracture. Okay, previously, of course, everybody knows this is well-known principle that for material without crack, but even with crack, here we show that this still holds. Okay, so with that, then I wanted to show that if you take a sample, okay, with some micro cracks in there, and maybe some microstructures in there, and I split that into 4. I have to make assumption what's going on the boundary. I'd assume that the displacements satisfy compatibility, and the traction satisfies equilibrium. Okay, so I do make that assumption. Now, if you do make this assumption, then this is a perturbation from this. Okay, so obviously from minimum potential energy principle, I now know this, the potential energy density, meaning divided by the volume, for this microstructure is larger than this. Right? So this is simply from the previous page. And if you then take into account of compatibility of displacements and equilibrium on the traction on the cell boundaries, then you can further reduce this to this inequality on the free energy. Okay, so I have a free energy. It shows here the free energy in this larger sample, density-wise, is smaller than the free energy of the smaller sample. Okay, then if you further link the free energy from the cracked microstructure to the free energy of this homogenized continuum through this damage parameter, go through some algebra, then you can show that there's an inequality here. What it says is that I have a larger sample, and I make the sample smaller and smaller. The larger sample are easier to fail. If I use the same damage law to describe the material, it depends on the sample you take. So there's a size effect. Bigger sample fail easier. And this is actually long time ago, Bazin talked about the size effect. I'll show you this relationship to his proposed size effect. But this is through.
But your definition of RVE would change, though.
Yeah, I mean, I take RVE. I didn't make any assumption. I assume RVE.
RVE basically would be, say, you need to take a size big enough that.
Yeah, but I'm not using asymptotic. You see, I'm using free energy. So I really don't have those restrictions. That's why I go this route instead of asymptotic expansion. Otherwise, yes, otherwise the scale separation would just kill you. Right? Okay, so we can show this by Monte Carlo just to show if this is really the case. Okay, so I have a Monte Carlo type modeling. I take a two-phase material. It's almost like a concrete material that you have a strong phase, which is the aggregates, and I have a weak phase, which is a cement. We assume there's a correlation between the strong phase and the weak phase because there's some sort of characteristic, some size distribution of aggregates, so they are not perfectly random. But anyway, introduce some sort of correlation, and you generate some samples, randomly generate samples with strong phase and with weak phase, okay? And then you apply, say, tension or shear, and you load the material, right? So for every sample, For every sample, I will take the bigger sample. I don't change the microstructure. Take a bigger sample, smaller sample, and smaller sample, right? And then you load it, you observe how it fails. You see, the bigger samples fail easier. Okay? So sort of consistent with the theoretical prediction. It really happens this way. You look at the damage curve at the given strand, the damage is higher statistically in the bigger samples than the smaller samples. So Monte Carlo does show you the similar trend. Bigger samples fail easier. So what do we do? So we try to use this to explain the mesh dependency. Okay, so this is sort of I know I'm going an unconventional route, but I think this offers a different explanation of why in damage mechanics there's mesh dependency numerical solution. Okay, so my explanation here is this. If I use the same damage law for continuum, and I construct a mesh, and I model it, and I apply the law until the structure fails, you refine the mesh, but using the same damage law, same material constants for the damage law. I'm trying to say here is that you will never converge, because, so for example, for a given mesh, suppose this is a mesh, and you use a damage law. Damage law is assigned to one mesh. From the relationship between the damage law and the underlying crack, I assume there's a sort of an underlying crack pattern that corresponds to that damage law. Okay? Now, if you split this into 4, and I already showed that this has a larger free energy than this. Okay? Now, with this, you can find an equivalent material with a larger crack that has the same free energy compared to this. Okay, so what it means here is that free energy here is bigger than this. So if I have a mesh that looks this big, and I use a damage law, I refine a mesh, I use the same damage law. Implicitly, what it implies is now I have a fracture pattern like this. You refine a mesh, you have a fracture pattern of this. And we know, as we just discussed, through derivation, you get smaller and smaller free energy. So as you continue to refine a mesh, we will not converge. And here's an example, right? I take a very simple elasticity problem, but assuming the stress up to a certain level, the material damage. Okay, so I take the sample like this, introduce the imperfection. Okay, so as you load it, the stress is not going to be uniform, but will be some concentration right here. I have small imperfections, so that the damage to initiate from here. Then I refine the mesh. Okay, I refine the mesh, make it refined and refined. And you apply the law. Every time you refine the mesh, this is the mesh, that's the localization zone. The strand is localized in this zone. Refine the mesh, you will localize into here. We further refine the mesh, localize into here. And you get completely different solution. Solution never converge. In fact, you keep refining it, this curve will curve back. So never converge. So you got to do something about it. Okay, and of course the explanation is different from what people have done before, but this has been observed for a very, very long time. So a lot of work being proposed to deal with the situation. Previously has been explained by the laws of ellipticity and all that. Famous work, a few examples here are to introduce the gradients of the strand as a regularization, as a so-called localization limiter to regularize this eopose problem. However, as you can imagine, if you have the strand, which is now higher order gradient included, and strand will be related to the stress and the equilibrium equation. That means the order of PD is increased. So you have to introduce additional boundary conditions, which is typically non-physical, right? So it's hard to explain how do you now, you have to introduce more boundary conditions simply on adding these higher order gradient terms in the strand, And I have to solve the equilibrium equation with these high order gradients in there, and that makes it sort of hard to even introduce additional boundary conditions. Also, in a finite element setting, how can you compute all these higher order gradients? So here, I'm extending the work of RKPM, and also in the earlier days, there's a work also from Wing-Kim Liu's group on something called a synchronized convergence. What they try to achieve at that time, for different purpose, but they try to achieve at that time is to hopefully construct approximation space such that, for example, convergence rate in H1 norm, it's about the same as a convergence rate in L2 norm. There may be some problems that you have such need, but at that time, that was the original idea, and they come up with an approach that, well, if you construct the first order derivative, which is what you measure the error in H1 norm, you construct in such a way that is still exactly reproduce polynomial of the gradient of the function at that level. Okay, so we use that idea and extend it to this, we call it implicit gradient. So let me explain the idea. I write it in the form of non-local because a lot of people here are working on thermodynamics, non-local mechanics. So suppose epsilon is a local strand and multiplied by this, you can call it non-local function, kernel function, and this is a non-local strand. Okay, so start from here. So the idea here is we would like to construct this kernel function such that this non-local strand represents the local strand plus any form of gradient, and that's the gradient term. Okay, so, and as you can see, this is the right-hand side is something that people have used before, but we try to construct this so that I can express that in the integral form. Previous talk in the morning talk, I forgot also talk about something like this, but use Fourier transform, right? But here it's entirely by construction. So construction-wise, you can do that. So this is how we can construct this. I'm taking 2D as an example, okay? But you can add a 3D term. So again, you express this by a kernel multiplied by some correction function, expressing this, right? And so, and this is a wave function. Again, you choose the smoothness you wish. Now, of course, if epsilon is any function, this is hard to achieve. But if epsilon is a monomial, then this can be done. Right? Then, of course, if I can impose this, then I have polynomial or monomial up to degree n. If it exactly satisfies this relationship, then you can estimate the truncation error. Okay? So that's the idea. Right? So I cannot make this to satisfy for any function, but I will make this to satisfy for monomials up to degree n. So you plug in monomials here, 2D or 3D, you add another term. You can rearrange the equation and write it in this way. Okay, and now you bring in this reproducing kernel by correction function and multiply the weight, put it in right here. Okay, so that's here. And what this means is really the moment equation, right? The first order moment, zeroth moment, first moment in x, y, z, and so on. So this is really the moment equations. That will allow you to solve for the coefficients, and you obtain this, and this M is really the moment matrix, is really the gram matrix of a set of bases with respect to this kernel, which is a positive function, right? So we know that, so if you have a bigger enough support, then this is invertible. Oh. Okay, good. Discontinuity. Okay, so through this, then you know that by construction of this kernel, you can now represent the local strand plus gradient of local strand and use this as a regularization of your post problem. Again, this will be exact if it is monomial up to degree n. If it is an arbitrary function, then just truncation, and this residual you can estimate simply by Taylor expansion. Right? Okay, so just a few examples. If I use zeros, just a constant term, this non-local strand becomes local strand. You use up to second order basis, then you can reproduce a second order gradient. Use to up to fourth order basis, you can reproduce fourth order gradient. And now, of course, here everything is expressed in terms of integral form. So then you think, well, for computation, I need discrete form. And discrete form will be just an approximation of this, so you have another error, right? So I don't want it to have another error. I would like to have a discrete form to also exactly satisfy. So that's another way to do it. I compare integral form and discrete form. So initially, non-local strand, I change it to discrete form. Simply do a Riemann sum on this. Okay, I don't even care about the weight because it just say that I wanted to reproduce this through this kernel by this summation. So that's my starting point. And everything else is the same. In the integral form, you want this integral convolution to generate this. I want this discrete form to generate exactly this. Right? So again, here you introduce a reproducing kernel. I introduce reproducing kernel. I want this to satisfy at the discrete level. So from there, then you obtain the coefficients B. The only difference now is this integral form of moment matrix. Now it's discrete form. This discrete is really a Riemann sum of this, exactly identical to this. So in the end, with discrete form, I'll be able to exactly reproduce the gradient if epsilon is a monomial. If not, then again, I have truncation, but you can estimate that, right? So this will allow me to exactly, so here's an example. If I have polynomials, and I wanted to reproduce polynomial plus a second order derivative plus fourth order derivative, and by this, right, by this gradient smoothing kernel, and I get exact solution. If something that is not polynomial, then I have a small error here, but still I think it's very close. I should have shown the numbers. I think mathematician I could see numbers. But anyway, here just to show that error is very small, you can assess that difference. Okay, so now you can bring this into an assumed strand. So this is my non-local strand. This is the reproducing kernel, and strand is a derivative of the displacement, bringing the approximation for the displacement. Anyway, my point is you can now express the non-local strand by a non-local, if you wish, gradient matrix multiplied by the displacement nodal value, right? And then now you have to bring. I should have expressed this by a variational equation and all that, but I just take a shortcut. Anyway, this becomes a mixed formulation. Then you have to be careful about the inf soup, the LBB condition. But anyway, in the end, you can now discretize the equilibrium equation by this assumed strand approach. So just to show you all these non-local, the non-conversion, as you refine the mesh in FEM, it tend to localize. Now it never happened. You have the same width of localization with this reproducing kernel strand gradient. The energy dissipation, dissipates more and more as you refine the mesh in FEM. Now it's all constants. The non-convergent solution now it's all convergent. Right? So here the same problem. Here now I have introduced the reproducing kernel strand gradient, and I'm getting converged solution as I refine the mesh. Another test problem, when the stress strain law, this is damaged beyond this point. And again, I'm getting not exactly perfect convergence, but they get very, very similar results as you refine the mesh. I get also, as mesh refine it, or as I perturb the nodes become non-uniform, I get pretty much very similar results. Okay, so, and as I said, we can actually link this to the size effect law been proposed long time ago, because Bazang also observed that material strength reduces as the sample size increases. And these are the data been measured, and he simply introduced a scaling law for that. Well, we can do the same thing. You either do the gradient regularization, or we can also modify that and introduce a scaling law for damage mechanics. Right? So with that, if you have a model that does not converge as you refine a mesh, with this, now they all give you the converged solution as you refine the mesh. So now I'm showing some engineering applications. The co-authors of this work is US Army. So we have developed a computational code based on what I have presented, and they use this for the modeling of impact penetration, bullet penetration over a concrete wall. This is a 3D calculation. I'm showing you the cross section. See, as the penetration come in from this side, it forms a shear band, and forms a shear cone. So in fact, the entrance side, the material damaged a lot more than the exit side damaged more than the entrance side, which is usually you think the other way around. It hits here, got to damage more on this side than the other side, but it's opposite. Because a compressive wave propagate, hit the free surface, become tensile wave, and damage more material on the other side. Comparison with some crack branching, but this is damage mechanics. I'm not using fracture. Fracture is just used to construct the damage law. Everything here is computed by damage mechanics obtained from the microstructure fracture mechanics calculation, right? And so this is the level of details that we can get through this kind of computation. We compare actually the damage zone on the exit side and entrance side compared to experiment. And as you can see, they agree actually quite well. This is the blue curve here is the experimental measured equator side. And we also compare the velocity. This is by computation. Experimentally only measure one velocity, which is the exit velocity of the bullet. But I think eventually computation agree quite well. Different wall thickness, different fracture pattern. And now you can model this, properly capture all the radial cracks, the circumferential cracks, and not a perfect, impossible, right? Because the material is so much variation, but this is experiment, and this is by computation. I think microstructure is done pre-computed, and then use the law. That's it.
Each RKPM particle, or just one for the material, and then you use the same curve every?
So you can. It depends on the approach. You can take different samples from different locations. You characterize different damage law and assign to different material points. Yes, that will be more ideal case. But here, no, we just use the same damage law for the whole domain. Okay, if the impact velocity is higher, is much higher than the wave velocity, then you get this polarization of materials. The material damage at the microscopic level. Right? This is computation. This is computation, and this is experimentation. You can apply that to, for example, landslide, shear band formation, and again, this is something that will be hard to model by the conventional FEM. It forms a primary, secondary, and the third order shear band. Okay, so in conclusion, I think we have introduced this damage model through microcrack calculation. We introduced regularization in computation and have been applied to some engineering problems. Okay, so with this, I conclude. Thank you.
Thank you, yes. Maybe one quick question. How does that work with the reception, Max? What time do we have to be where?
I'm not in charge of the reception.
So let's see. It's in the program, right?
Yeah.
What's in
You should have a look outside before you can answer.
I don't know.
So we can ask a lot of questions.
Yeah, go ahead.
It's very nice talk. For your implicit gradient,
Yes.
for the calculation, how do you pick the constants? That's a problem.
Yeah, well, the constants, yes. That's $1 million question, yes. Constants have to come, it's like in shear band, when they have to introduce the length scale as a localization limit, they have to measure that experimental.
In practice,
Yes.
you have many length scales. So
Yes, you have to.
Can you actually use the experiment to match the length scale?
That's something that we try to work out, is to actually experimentally measure the shear band width and then correlate that to the microstructure of the material.
So that is
That's-
like a matching.
Yes, you can only do that by experiment to characterize those constants.
No more questions. There's a reception.
Great, I'm relieved.
It is